To continue our training, we are going to be changing modules at this time, and we are going to talk about electronic expansion valves. I don't know if you have already come across these valves, but so that you can recognize them visually, they are like this. They are not only solenoid valves that open and close, but they are expansion valves that are constantly varying the flow of refrigerant that they let pass through. So, the errors they present, the measurements we are going to make, how they work, we are going to be analyzing it now. For those who still don't know, they didn't realize, this expansion valve replaces the capillary in conventional equipment. In inverters as well, more conventional or of lower quality, there is still capillary, but in the best ones we already have expansion valves, such as in Carrier or Myers. How does this valve work? Well, but in you who have 6 connection cables to the board, these 6 connection cables are basically as follows. Look, we have 2 cables that are negative 12 volts, and then what we have are 4 more cables that are going to be injecting the positives, and with that they are going to be closing the circuit in the coils. One moment, I'll find you a diagram with which we will understand it perfectly. Basically, they are 4 coils. They are 4 coils that are energized with 12 volts through pulses, and they are going to close circuits. For example, we will be injecting electricity through the brown and red. And when we want to rotate each of these coils, the board will give pulses to the white cable, the orange cable, the blue cable, or the yellow cable. As it gives pulses, it is causing electrons to circulate through one after the other, and after the other. It works like a small stepper motor. It works exactly the same as the air oscillating motors of the previous unit. Do you remember this air oscillating motor? In the same way these expansion valves work, allowing the board to control the exact position in which the rotor is located. These usually had 5, and this is because one of the 2 was shared. Red was also brown. Red and brown were together, which would be the same in the end. But in the valve to have more control yet, it has 1 more, that is 6. How do we understand its operation? Understand that it does it through pulses. That is, the board does not send a constant 12-volt signal, it sends pulses. And when it sends pulses, it makes the motor go around, very fast pulses. That is why, if we inject 12 volts directly and fluids and clean, it may be that this component burns out. If the valve does not work, the first thing we will do is test the electrical or electronic part, which is composed, obviously, of the wires and also of the winding that is placed on the top. If you look closely, it has a way to turn and remove, very similar to how we removed the coil of the hot-cold valve of the 4-way valve. It is removed, and we can remove the electrical or electronic part. This electrical or electronic part has a simple measurement that we can do, and it is through ohms. If we control and measure, for example, between white and red, obviously we are measuring the winding of this coil. Then between white and red it will give us a result of 43 ohms. These ohm results are similar in all valves. They are not exactly like that, but they are very similar. Now, if I control between yellow and blue, look that I am traveling 2 coils. In that case, between yellow and blue, the resistance will be double, 85 ohms. And so with all, between orange and red, between brown and blue, between brown and yellow, and between orange and white. To measure double, in all measurements, I will have to have results like these that will be given by the number of coils that I am controlling. Well, this is the main way to be able to measure it, and it is an electrical/electronic way without voltage. Let's watch a short video where it shows us the measurement we did. Here we are seeing how we do that measurement. Look, we have 90.8 or 9 ohms. In another one, there are 45.6 ohms in one of the coils. There is nothing there. We also have to control between the ones that are opposite to know that we do not have any false measurement. That is, the coils may also be short-circuited, so we have to measure between the ones that are separated to see that the travel is open line. In the next measurement, we have another coil. And that's how we keep going through all of them. I am letting you know that the link to these files is in the video description so you can download them. You saw that the values will be approximate. A moment ago, in the measurement we made on that carrier valve, we were talking about having 90 at this point, and here we had 45, approximate to this example. Very well, this with respect to the electrical/electronic part of the expansion valve. But, do we have another part in the valve? Yes, we have the mechanical part that lets in and out the refrigerant, and that is where we have to be more careful, or rather, it is the most complicated to repair, because to replace that valve you have to solder and unsolder. So, let's say that we have a problem or a defect in the mechanical part of that valve, that is, the part that allows the refrigerant to enter and exit. How are we going to detect the problem? Since the equipment will not mark us an error of electronic expansion valve. We will not have that error in the equipment. In reality, detecting this error in an inverter unit depends 100% on your knowledge and understanding of how a unit works. Think that if this valve is staying closed too much, the internal and external pressures will vary, as well as the discharge temperatures of the compressor, and the equipment will mark an error, for example, excessive overheating, excessive supercooling, excess compressor discharge temperature. They are rare errors that usually have to do with the refrigerant, up to lack of refrigerant. All of these errors can be indicating a defective expansion valve. Of course, this depends solely and exclusively on us to be able to detect that error. Some errors are excessive overheating, excessive supercooling, excessive compressor temperature, and lack of refrigerant. They are errors if the valve opens or closes too much. But we have a way to test the electronic part of the valve. It would be to disassemble and remove this part of the valve, the electrical part. And inside it, we can place a screwdriver. When placing a screwdriver and allowing the valve to activate by turning on the motor, or with a universal board, that screwdriver will move because it will stick to the different walls of the valve. This is an electronic or electrical way to test it. Energizing the valve, we place the screwdriver inside and it has to stick to the edges. Now, if we see that the entire electrical part works well but still has an error, temperature, or strange pressure, well, it is time to think that the problem may be here, in the mechanical part. A quick way to see if this turn works or not is when we energize inverter units. In general, the valve makes a complete opening and closes again. So, at the time of energizing, we have to hear the noise of the electronic valve rotating, which would indicate that it is in good condition. We have to hear the noise of the opening and closing. It sounds like a knocking noise, something like that to understand it. If we still notice that there are defects, something that we can do in some cases, it works in others, is with a magnet, with a strong magnet, perhaps those that are used to recover fallen screws. Without the electronic part in place, with that magnet, move it around the valve and see if the valve rotates, activates, or does anything. Move it around the valve to see what happens. Because it is very sensitive to the small magnetization, it rotates or moves. So you have to move it around and see what happens. Sometimes it can open a little and see how the refrigerant pressures vary. Now, if all this still does not work, well, we have to be thinking of replacing the electronic expansion valve. In that case, what we will be doing is applying the following tips. You saw that the valve has the electronic part and the welded part. And you will see here that the space from the weld to the valve is very short. What is the problem? The problem is that in order to solder this valve, we have to completely wrap it, of course, without the electronic part connected because we are going to remove it, but the mechanical part we have to wrap completely with a damp cloth so that it does not overheat. That damp cloth must be made of cotton and be constantly wet. In fact, if you have an assistant who is sprinkling water on it while you are soldering at these points. The problem is that the position of the valve is always like this, standing, and when you wrap it with the cloth, it drips and cools the weld, which makes it take longer to solder and the heat reaches the valve and can damage it. A tip from me is, originally we have it in this position, and at this point we have to solder. And here the air conditioner continues, these pipes will continue and will go around below and go to different parts of the piping. What can you do instead of soldering at these points? Well, when you buy the expansion valve, you can place it on its side where you can wrap it better with a cloth with water, and solder some longer pipe sections, and leave your expansion valve with longer pipe sections. So, what will you achieve? Well, when you are going to place it in the equipment, the welding you will do on the equipment will already be much lower, because you will cut the pipes here, because your expansion valve already has longer sections in place. Unfortunately, they come with very short pipes that make it quite difficult for us, but if you take the time to add these sections, you will surely find it much easier to solder because you will be able to wrap it with a damp cloth without problem, and you will be away from the welding area, which is this. A very important detail is that all this is always welded with an atmosphere of extra dry nitrogen. I don't know if you know or not what this is, but all this has to be welded with a certain amount of nitrogen passing through the pipe constantly to prevent the formation of the common slag when we weld. When we weld a pipe, what always happens is that at the weld point, we clearly see that a certain slag or residues are formed that are the fault of the burning of oxygen together with moisture. The same thing happens inside. Now, by sending a constant atmosphere of extra dry nitrogen during welding, we prevent the formation of that slag inside. And so we have a clean weld inside, which then, when the refrigerant is circulating, will not drag those residues inside and clog another component such as the expansion valve itself. So, always with the atmosphere of extra dry nitrogen. Later, I might leave a video explaining this. It is not necessary to explain it in inverter refrigeration because it is not specifically about inverter refrigeration. In reality, it always had to be like this, but in inverter it is more than necessary because we have equipment with 410, with 32 which are more delicate gases of which we have to be careful of all those residues that remain inside the pipe. Well, this is what has to do with electronic expansion valves. I will briefly show on the board how this valve is connected. Here we have a board with a slot for the expansion valve. In fact, it doesn't have the slot, it just has the slot because this model didn't come with it, but look at the following. In this point, we have an electronic expansion valve, which connects to these 6 terminals. And these 6 terminals go to a driver, which is a series of electronic valves that act as communication between the processor and the valve. That is, the processor does not directly control the 12 volts of the valve, but does so through a driver, a series of pass valves. We can say that it is something like a small IPM. And they give the valve pulses as they want. There are several electronic pass valves that allow the 12 volts to pass directly, commanded by a much lower voltage that comes from the microprocessor. In this model we do not have it installed because this model does not have it, so neither the socket to connect the valve nor the driver is installed. But that's how it's controlled. We could measure the pulse emitted by the board with an oscilloscope in case it were the board that brings it, but well, this area does not usually fail. Most of the failures are in the valve itself. And one more detail to keep in mind that I mentioned, and then we will see. To be able to control an expansion valve correctly, you will need a universal board. With a universal board, we also have the possibility of testing electronic expansion valves. So that's where we get to the topic of expansion valves. Please leave a comment if you have any questions.